Swayam Prabha. Digital India. Educated India.
Hi friends, now we will have a tutorial session, and in this session we will solve some numerical problems based on our discussion in the last 4 classes. The first problem says a vacuum residue has the following properties: that condensation carbon ratio CCR is 15 weight percent, API gravity 8.5 degree API and sulfur content 3.0 weight percent. It is fed into a delayed cooker at a rate of 2 lakhs pound per hour. Determine the production rate of gas, naphtha, VGO and coke on the basis of empirical formula. If the sulfur is distributed in the gas, naphtha, VGO and coke products as 30%, 5%, 35% and 30% respectively, find out the concentration of sulfur in these products. So, this is a problem based on delayed cooking, and it is the properties of the feedstock is given, that is CCR, API both are given and sulfur content is also given. Now, after the delayed cooking we will be getting different products, that gas products we will get naphtha, we will get VGO and we will get coke. So, these are the major products of the delayed cooking process, and then we have to find out the sulfur content in this, and relative amount of different products is already given. So, 30% for gas, 5% for naphtha, 35 for VGO and 30% for coke. So, we have to solve the problem. So, now we will see what data is given. We have feed rate 2 lakhs pound per hour, and then CCR is 15% and sulfur is 3% in the feed, and API is 8.5 for the feed. So, then what we will do? We will use the empirical relationship to determine different products, as you have discussed in our previous classes, that using some empirical formula we can predict what will be the product distribution for a delayed cooking process. So, here we had this expression gas equal to 7.8 plus 0.144 into CR percentage, the weight percentage of CR. If we put here, then we will get, by using this formula we can get the gas weight percent, how much gas it will be produced, and accordingly we can get the production rate also, the how many pound per hour. So, in this case what is the CCR? In our case we have 15%. So, 15, if we put 15 into 0.144 into 7.8, that is equal to 9.96, and then 9.96, this is in percent, gas in percent. So, that is equal to 9.996 percentage. So, how much we had? We had 2 lakhs. So, 2 lakhs per hour, 2 lakhs per hour we had 2 lakhs pound per hour. So, 2 lakhs pound into this percent, that is 0.0996, that is equal to 19,920 pound per hour. Then for the naphtha, this is equal to, what will be the percentage of that? The 11.29 plus 0.343 into CCR weight percent. So, here we will put 15 and we will apply this formula, we are getting 16.44 weight percent. So, again we will multiply with the actual feed and then we will multiply this percent with it, and we are getting 32,880 pound per hour. Similarly, for coke we had the empirical relationship, if that is equal to coke in percentage, that is equal to 1.6 into CCR in weight percent. So, 1.6 into 15. So, we are getting 24 weight percent. So, that is equivalent to 48,000 pound per hour, and gas oil we can calculate by the difference. So, 100%, that is also in percentage. So, 100 minus gas percentage minus naphtha percentage minus coke percentage. So, we will be getting 100 minus 9.96 minus 16.44 minus 24. So, that is equal to 49.60, and that is equivalent to 99,200 pound per hour. So, now we are getting, by summing up, we are getting 100%, and this is our product distribution. This is the pattern of the distribution of the products, and then this is the total amount the product is formed, that is equal to 2 lakhs pound per hour, and this is in mass basis, the distribution of different products. Then we have to find out sulfur in these products. So, how much sulfur we had originally? It is given the 3% in the feed. So, 2 lakhs into 0.03, that is equal to 6,000 pound sulfur is present in it. So, here the basis is say 1 hour operation, 1 hour operation. So, if the plant operates 1 hour, then it will consume 2 lakhs pound of feedstock, and that will be having 6,000 pound of sulfur. Then we will see what is the sulfur in gas. So, we have 6,000 into 30% sulfur is coming as it is given, total sulfur which was in the feed, 30% is coming to the gas, and then 5% to naphtha, then 35% to VGO, and again 30% to coke. So, this data we will be using. So, how much sulfur we had and how much, what is the percentage of that sulfur transferred to a particular type of product, that we will consider. So, in this case we had 6,000 pound of gas production per hour, and 30% sulfur is coming here, that 30% of sulfur is converted. So, we are 0.3, so it is 1800 pound we are getting here, and then sulfur in naphtha, that is equal to 6,000. Originally 6,000 pound sulfur was present in the feed. So, 30% is converted to gas, it come into the gas. So, that is the gas sulfur content is 1800 Lb, that is 6,000 into 30%, 0.03, and for naphtha 6,000 total amount of sulfur present in the feed into the how many percentage is converted to, it transferred into naphtha, that is 5%. So, 6,000 into 0.05, that is equal to 300 pound, and for VGO it is again 6,000 into 35%. So, 0.35, that is equal to 2100 pound, and for coke 6,000 into 0.03, so 1800 pound. So, these are the mass of the sulfur present in different product stream. Then what will be the percentage? So, then we can convert it into percentage, because we have already calculated what will be the mass of different products we are getting through this process in 1 hour. So, then concentration of sulfur in gas will be, this is the sulfur in the gas, and this is the total mass of the gas. So, this sulfur, mass of sulfur by mass of gas into 100, that is the percentage of sulfur in the gas stream. Similarly, the concentration of sulfur in naphtha, that is the mass of naphtha in the mass of sulfur in naphtha divided by mass of naphtha into 100. So, again 0.91%, and then concentration of sulfur in VGO, mass of sulfur in VGO divided by mass of VGO into 100. So, 2.12%, and for coke again the sulfur in coke, that is equal to 1800 divided by total mass of coke 48,000 into 100. So, 3.75%. So, now we are able to determine that what will be the product distribution and how the sulfur will be distributed in different products. Now, we are coming to the next problem. So, problem 2, it says that it is required to decoke a vis breaker coil with an inside diameter as 9 centimeter and 700 meter long with a coke layer of 0.35 centimeter thickness. This is done in two steps. First step, air is introduced to combust the coke layer whose density is 1202 kg per meter cube. In the second step, steam at 450 degree centigrade and flow rate of 1000 kg per hour is introduced to the coil to remove debris and cleaning up. The exit temperature is 700 degree centigrade. Coke contains 92% carbon and 8% sulfur. So, these are the data provided. Then for how long should steam be switched on in hours? We can assume that specific heat of steam is 2.13 kilojoule per kg per degree centigrade. Heat of carbon combustion, the combustion of carbon, that is equal to 32,770 kilojoule per kg, and then heat of sulfur combustion 9300 kilojoule per kg. So, this information is given to us. Then what we have to do? We have to calculate what is the time required to pass steam through the coil. So, this problem is related on the vis braking. So, in vis braking we have coil say. So, here we are giving feed in this is product out, say in and out. So, here the diameter of this, say if we take some part of it, this part, so it will be like this. So, it has diameter of 9 centimeter, and inside this diameter there are some coke deposition during the vis braking process. Both sides there will be some coke deposition inside the tube. So, this thickness is 0.35 centimeter and this length is equal to 7 meter. So, this is the problem statement. Now, once the vis braking is completed, the coke deposition has taken place. So, if we want to use this coil again, so we have to remove the coke from the inside of the coil. So, this can be done by providing air. So, what the air will do? That C plus O2, that will be CO2. So, this reaction will take place, and during this reaction heat will be generated, and that heat will be taken up by the steam, as the steam inlet temperature is equal to 450 degree centigrade, and then when it is going out, then the temperature is coming to 700 degree centigrade. So, heat released by this reaction by the coke will be taken up by the steam, and then its temperature will increase. So, if we do the energy balance, then we can be able to calculate the energy transferred from this reaction to the steam, and accordingly we can calculate the what will be the time required to flow the steam. As we have steam flow rate, it is given, and specific heat is also given, and combustion for this reaction is also given, and again if sulfur is present, so sulfur will also be react with oxygen and it will give us SO2. So, that del H is also given. So, this is a energy balance problem. So, we will solve it now. So, volume of the coke layer we can calculate, as you have told that this is the case. So, we have the layer. So, what will be the volume of this layer we can calculate. So, we have this is diameter and this is equal to say thickness d, and there the thickness is small and we can approximate, and this is equal to say 7 meter L. So, 2 pi R L into H. So, this is equal to say H. So, 2 pi R L into H, this will be the volume, or pi d L H. D is the diameter, where R is the radius, these are same. So, radius, here we are having diameter. So, pi dl into h. So, this formula pi 3.14 into 9 centimeter. So, converted to meter 0.09 meter. So, d now we are having L, it is also given 700 meter long. So, this is equal to 700 and this is not 7, this is 700 meter. So, 700 meter and then this equal to the thickness, this thickness h. So, this thickness. So, this is the volume of this coke layer. So, how much coke was deposited in volume, this is. Then what will be the weight of this, that is equal to basically mass of this, we can say mass of coke is equal to volume into its density. Density is given, that is equal to 1202 kg per meter cube, it was given. So, multiply this into 1202 into 0.6924, that is equal to 832.2 kg. So, this amount of coke is deposited inside the coil. Then heat of combustion of coke, what will be the heat of combustion of coke? Because this coke has carbon and sulfur, 92% carbon and 8% sulfur, it is given. So, what is the mass of coke we are getting? 0.92 of that will be the mass of carbon and that will be combusted to CO2. So, for that del H value is equal to 32770 kilojoule per kg. So, now we are having the total mass in kg. So, multiply it by this. So, we are getting 2.5 into 1 into 10 to the power 6 kilojoule by approximation it is. And then heat of sulfur combustion in coke. So, how much sulfur is present here? 8%. So, total mass of the coke into 0.08, that is the mass of the sulfur. Then the heat released due to the combustion of sulfur to sulfur dioxide. So, that is multiplied 9300. So, we are giving 0.62 into 10 to the power 6 kilojoule. So, what is the total heat released by these two reactions? This plus this one. So, we are getting 25.72 into 10 to the power 6 kilojoule. So, this is heat released by the combustion reaction. Now, this is taken up by the steam. So, if we consider that M is given, say M is mass of the flow rate of steam, M is mass flow rate of steam, then m Cp dt, m Cp dt del T, T out minus T in del T, that is equal to T out minus T in, temperature difference into mass of steam into Cp, average specific heat of steam. Then we will be having this Cs, and if we can use this formula and put the value of this, we can get the rate of heat gain by steam, because this mass is related to the mass flow rate. So, that is the heat flow rate will be MSCS and T out minus T in. So, in this case what is our MS? It is given 1000 kg per hour, 1000 kg per hour steam it is given. So, 1000 we are putting, then CS it is given, how much it is? 2.13 kilojoule per kg per degree centigrade. So, we will put this value here, and then temperature difference how much? 700 output and input 450. So, 700 minus 450. So, then we are getting 0.53 into 10 to the power 6 kilojoule per hour. So, this is the heat taken up by the steam per hour, but how much steam, how much heat has to be taken up by the steam? This much. So, what will be the time required to transfer the total heat generated during oxidation process to the steam? That will be 2572 into 10 to the power 6 divided by 0.53 into 10 to the power 6. So, that is equal to 48.5 hour. So, 48.5 hour the steam switch has to be kept on. Next problem. So, now we are coming to problem number 3. So, this problem says gas oil with API gravity of 30, 1 barrel contains 306 pound and a sulfur content of 1.5 weight basis is fed into a hydrotreater. It is required to carry out hydrodesulfurization at a severity of 90%. Calculate the hydrogen required and the API gravity of the product. The amount of hydrogen required can be calculated based on correlation given as SCF hydrogen per barrel is equal to 110.8 into SF plus 10.2 into SDS in percentage minus 659. So, this SF is the weight percentage of sulfur in the feed and HDS is the percent of hydrodesulfurization required, that is degree of severity. The increase in product API can be calculated as del API P, that is equal to 0.00297 into SCF H2 by barrel minus 0.11205 API of feed, 0.11205 API of feed plus 5.5419. So, this empirical relationship is given, we can use it to calculate the changes in API due to this process. So, this equation is used for feed sulfur content of 0 to 6.0 weight percent. So, in our case 1.5 weight percent is provided. So, this formula we can use to calculate the API change due to this process, and what is the hydrogen requirement, that can also be calculated by this empirical formula. So, we are going to do that. So, how we will do it? We are assuming that 1 barrel of gas oil. So, API is equal to 30, that means 306 pound per barrel it is provided. What will be the sulfur in feed? 15% it is. So, we have 306 pound into 0.15. So, 4.6 pound per barrel feed we are having that sulfur. Then what will be the total hydrogen required? SCF B H2, that is equal to, it is given, this formula is given. So, 110.8 into SF. So, it here SF equal to 1.5 and then 10.2 into degree of severity, that it is given 90%. So, 90% severity is required. So, we will be putting here 90 minus 659, it is coming to 425 SCF per barrel, and del API for the product formation we are getting 0.00297 into, this was given SCF, and then 0.11205 into, what is this? This 30 is equal to API, how much API the feed has. So, this plus 5.5419 it is given. So, that is coming equal to 3.4. So, 3.4 del API is changing. So, what will be the product? So, 30 plus 3.4, 33.4. Okay. So, degree API is increasing, that means the product is becoming lighter. Through hydroprocessing the products become lighter. Next problem statement says 100 pound per hour residue was introduced to a de-asphalting process which operates at 220 degree Fahrenheit. The residue has the following properties: degree API 6.6, degree API 6.6, sulfur content 4.8%. A solvent enters the process at a rate of 600 barrel per hour. The DAO, that is de-asphalted oil produced has degree API of 19.8. Calculate the yield of DAO and its sulfur content in weight percent. It is given at 220 degree Fahrenheit, the DAO weight percent is equal to 45% of the residue. It can be assumed that the percent sulfur in DAO is related with the yield of DAO production. The sulfur in DAO may be around 30% of its amount in original feed, when the DAO yield is around 50 volume percent. So, this is a problem statement. So, what we have to do? We have to calculate the yield of DAO and we have to calculate the sulfur content in it in weight basis or mass basis. So, here what is the solvent to oil ratio? 600 pound per hour and we have 100 pound per hour residue and solvent is 600 pound per hour. So, what is the ratio? 600 divided by 100. So, that is 6 and then what is the DAO? How much DAO is produced? That is equal to 45% is residual part is coming as DAO. So, 0.05 into 100. So, 45 pound per hour. So, this is our DAO production, the first part is done and then DAO which is produced, what is the API? Degree API is 19.8. So, that is equal to SG of 0.935. What is this? Degree API equal to 141.5 divided by specific gravity minus 131.5 as we have discussed. So, here in this case API is available, that is equal to 19.8. So, SG we can calculate by this expression and that is equal to 0.935 and residue API equal to 9.9 as already given. So, in that case we can get the SG also by using this formula. So, it is coming 1.0246. So, specific gravity of feed and specific gravity of product we are able to calculate. Then what will be the percentage yield? That is equal to 45 divided by specific gravity of it, that will be the volume, 45 is the mass, so divided by this. So, it is the volume of the DAO and then what was the total volume of the residue, that is equal to 100 was the mass and then divided by this specific gravity, that is the volume. So, this volume of DAO divided by volume of the residue or the feedstock into 100. So, 49.3% DAO yield. Now, it is given that sulfur content is dependent on that DAO yield and it is also given if DAO yield is around 50%, the sulfur 30% of sulfur will be transferred to DAO. So, we are having here sulfur present in DAO is equal to, we have 4.8 LB into 0.3 because we have 4.8% sulfur was originally present in feedstock. So, 30% of it is being converted. So, that is equal to 1.44 pound is coming to the DAO. So, then what will be the weight percentage of sulfur in DAO? That is this into the, this is divided by 45 into 100, the mass of sulfur divided the mass of DAO into 100. So, that is the percentage of 3.2%. So, that was we are asked to calculate and we are able to solve it. Our next problem is a feed of VGO of 37,500 BPCD, that is barrel per calendar day, is hydrocracked to maximize the ATK, aviation turbine kerosene production using 3 weight percent hydrogen. The API of the feed is 20 and the mean average boiling point, that is TB is equal to 575 degree Fahrenheit. The process produces gases, gasoline, heavy naphtha and ATK. Make material balance around this hydrocracker, the following correlations can be used. So, hydrocracking severity we can calculate by using this correlations, that is 0.6621 into H into Sg, where H is the weight percent of hydrogen added and Sg is the specific gravity and then Vh is the cubic feet of hydrogen produced per barrel of feed, and gasoline liquid yield can be calculated by this empirical relationship, that is volume percent, that is liquid volume percent, that is equal to this one minus 0.03734 into APIF feed API square plus 1.57575 APIF plus 0.14923 K minus 1.36473 VH minus VH by K. So, VH already it is given and then K can be calculated by TB to the power 1/3 by Sg and this TB in Rankine's scale. and butane productions in volume percent we can calculate by this empirical relationship. These productions will be dependent on the liquid volume percent of gasoline and API of the feed. Similarly, heavy naphtha can be, the liquid volume of heavy naphtha can be computed by this empirical relationship, which is based on the gasoline percentage and API of the feed. Okay. The following equation can be used to convert liquid volume percent to weight percent for hydrocarbon products, that is product in weight percent is equal to 0.8672 into product in liquid volume percent minus 0.9967. So, this is the problem statement. Now, we have to do a mass balance of this. So, from feed API of 20, the specific gravity we can calculate 0.934, the same expressions, the specific gravity equal to 141.5 divided specific gravity, sorry, API equal to 141.5 by specific gravity minus 131.5, the same formula we can use. And then hydrogen we have 3% we are adding in this case, then VH will be how much, 0.6621 into 3 into 0.934, because this into sulfur content SF into specific gravity. So, we are getting 1.855 feet cube per barrel, and then K is equal to TB to the power 1/3 divided by SG. So, TB in Rankine. So, this was 575 Fahrenheit. So, plus 460, that is in Rankine to the power 1/3 by this. So, that is equal to 10.83. Then what will be the gasoline liquid volume? This empirical formula we will put. So, this is API of the feed, and then this is feed, and this empirical formula we are already given, this is equal to K value. So, we are putting the empirical formula and we are getting the value of 14.18 liquid volume percent, and gasoline weight percent equal to how much? We will put that relationship which is given to convert volume percent to weight percent, that is 0.8672 into 14.14, that is 14.14 is the liquid volume percent minus 0.9969. So, it is coming 11.30%. Similarly, for gas, what will be the liquid volume percent? So, this one we will be putting the same expressions as provided. So, we are getting the value of 5.04%, and for heavy naphtha LV percent is equal to this expressions we had, that is the gasoline production and then degree F feed APIF. So, then we are getting 19.94%, and weight percent if we want to convert, then this volume percent into this minus this, already the expression is given. So, I am getting 16.29% for heavy naphtha. For ATK we are getting 100, we have the feed plus 3 hydrogen we are adding, then we are getting the difference of this is the difference of other masses, different, this is our input, this is our mass of the feedstock, this is our mass of other products. So, remaining is the mass of the ATK weight percent, that way you can calculate, and this is the summary of the material balance. VG we have, hydrogen we are adding, so to 103 we are getting, and then we are getting the products, this one gasoline and this one and this total 103. So, mass balance we are getting. So, up to this in this class, thank you very much for your patience.